Right, welcome everybody to the June 2025 meeting of the Mornington Peninsula Astronomical Society. And as usual, some of the things that have been in the literature in the last month shown here. First one in the top left here is Murray Young, which is the indigenous name for the Parkes Radio Telescope, if you hadn't heard that before. It's undergoing its 20-year maintenance at the moment of its gearboxes and bearings. So you see it's in its park position where the dish is actually stored horizontally, which minimises the angle to the wind. And they lift the dish up by a couple of millimetres, just enough for them to get the bearings and the gears out. So some pretty serious hydraulic jacking goes on to get that up. So it takes them about 4 or 5 weeks to actually take everything out and re-grease them and refit them again before lowering the dish back down. So you hope it's... oops, someone just turned the lights out. You might want to turn the middle ones on, otherwise we'll disappear. So it takes them about 4 or 5 weeks to actually replace them all. So that's why they only do it about once every 20 years. And they hope that it doesn't get particularly windy in the meantime, I assume, as well, while they have it disengaged like that. Moving on to the next one across, the top in the middle. It's now been discovered that the Milky Way the spiral arms come out not from the centre of the Milky Way. If you remember, the Milky Way has like a bar across the middle of it, a small bar. The spirals were thought to actually come from the ends of that bar, but they now have revised that. They've actually found stars going in orbit in a circular direction, in an oval direction around it, elliptical direction, and the bars actually come from the edge of that oval, strangely enough. So they've revised that view of what the centre of the Milky Way galaxy looks like. Over on the top right-hand side, Canada is actually now set to launch its own low Earth orbit constellation, a bit like the US's Starlink satellites. And it's due to be called Telesat Lightspeed when it begins launching next year. Amazon has already started their constellation of 3,200 satellites going up, and they've only just started putting those up, but they have launched a couple up already, so it's going to get mighty crowded in the sky for Earth-based observers trying to look past them. And it's thought that the Canadian one is likely to be what Australia uses to replace the MBN satellites, which are very, very large satellites called Sky Muster, but they're in geosynchronous orbit, so they're quite far out from the Earth's surface, whereas these are low Earth orbit satellites, so more likely to be at the height of the space station or thereabouts. So probably I would say Elon Musk and Donald Trump haven't helped their cause there in any way, because they're seen as being somewhat unreliable. Down in the bottom left-hand side there, you might have heard the term SETI before, the Search for Extraterrestrial Intelligence. There's now a group being set up called Whale SETI, whereby, associated with the SETI program, whereby they're going to try and decode some of the behaviour of humpback whales, to see if they can figure out what they're trying to tell humans, because they've been observing that during human interactions, the whales will release these circular bubbles in the water as they're interacting with the people. And you take the people away and you fly drones over them and try and interact them with other species, and they don't do it. So they think it's some form of communication, is the theory. And now they're going to be using the principles that they're looking for searching for intelligence in signals coming from deep space, to see if they can actually understand what's going on. And you'd have to say, probably a good idea, if you can't actually understand and communicate with life form on your own planet, that what hope do you have with one on another planet? So that's underway. In the middle there, everyone probably knows that the Andromeda Galaxy was thought to be on a collision course with the Milky Way in about 5 billion years' time. A more detailed study of the Gaia data and Hubble Space Telescope data have actually done 100,000 simulations of that collision, and they actually find that it's only about a 50% chance of Andromeda colliding with the Milky Way galaxy in the future, and it will be about 10 billion years in the future. Otherwise, so that means it's 50% chance that it will pass at a sufficiently large distance away that it will miss us entirely and either keep going or potentially turn around at a much longer time in the future and then merge back, which will turn the two of us into some sort of an oval-shaped galaxy, an elliptical type galaxy instead. Now they do actually, from the simulations, they know the Large Magellanic Cloud will collide with us in about 2 billion years. And what they did in these simulations was they looked at the gravitational effect of all the neighbouring galaxies in our local group to try and work it out a bit more accurately. And so it's only now going to be, as I say, a 50-50 chance that Andromeda will collide with us. And finally, over on the bottom right-hand side, the Japanese tried a second time to land on the surface of the moon with their Regolith lander. It was called Resilience. Unfortunately, it didn't prove to be too resilient. And it also had on board a rover called Tenacious. And to quote what they said, it hard landed on the moon, which meant that it crashed. And unfortunately, in Mare Frigoris on the moon, and that was pretty much the end of it. It lost all communications with the moon, and it's just sitting there. And they think it's an issue with the laser ranger finder that was used to determine the height between the craft and the surface. So all reliant on that one little thing, but at least there wasn't anybody on board. So you would hope that they would iron that out before people started going. All right, tonight, so welcome to the meeting and welcome to any new members. I don't have a list of the new members since our last meeting because our secretary's not here tonight. So if there are any members who've joined in the last month, welcome to the Society. And if you need to say hello to anybody, I'll get any committee members here to put their hand up so you can have a look around. Feel free to come up and say hello, say during the tea break or any time during the evening to ask anything there, or even up to me if I'm not looking too busy. As usual, I'll go through the events past month and coming month, and I'll throw over to Chris for the monthly photo challenge, and then Guido for Sky for the month. Then we'll look at the theme of the sun, so we'll be talking about touching the sun. And that's being given by Professor Chris Lintott from the UK. And then from his PhD student, Dr.Becky Smethurst, we'll look at how long is the sun going to last for and how did they actually arrive at that number, which is 5 billion years is the answer, but how did they actually work it out? And they'll explain that in some detail, and it really is quite interesting, based on centuries of understanding. Then we'll look at how the European Space Agency's Solar Orbiter, which you might have heard in the news fairly recently, and the NASA Parker Solar Probe work together. And you might have heard on the news that the Solar Orbiter took the first pictures of the sun's south pole because it's been specifically designed to have a view of the south and the north pole. It's not the first spacecraft to actually go over the south and the north pole. The first one to do so was the Ulysses spacecraft, the European Space Agency's Ulysses spacecraft. This is a Lego version of the spacecraft, and I'm pretty impressed how they can send Lego that close to the sun as well and survive. It's only about 3 metres tall, right? So it's a relatively small craft compared to the later ones, the Solar Orbiter and the NASA Solar Parker Probe as well going there. That spacecraft didn't have any cameras on it, so they couldn't actually image the sun as they were going over. So it was all radio and magnetic instrumentation on board. So it was just data coming back rather than actual visual data. And then we'll close with the view of the South Pole from the Solar Orbiter as it went over earlier in the month. So recent events, shown in the background there is some of you may have seen Phil Holt's lovely image there of the Aurora Australis from his backyard in Mornington. It was a fairly weak KP value at the time, on the 13th of June, so a few days ago, just using an ordinary Pentax digital camera. All right, so in the last month, 24th of May, we had the Working Bee and barbecue here at the Briars. Then a couple of days later, we had the Langwarrin Guides here during the Scouts, Cubs and Guides night. They were the only group to book in that night, so they basically had us all to themselves. We had 23 there, and unfortunately they had total cloud cover all evening, so they didn't get to see terribly much. Then we had the committee meeting a few days after that, talking mainly about the special general meeting and replacing the chairs that you're sitting on. So the ones that you're sitting on have not been replaced yet, but we're underway to get a whole new set of chairs that are going to be designed to hold more up-to-date mass of people. Well, we have a couple of the new chairs actually at the back there behind Phil. So we've got 6 or 7 of there if you want to give them a try. They're rated at 200 kilograms, so don't eat up especially to give them a test. They should be able to fit 2 people per chair, yeah. On the 6th of June, we had Trevor talking in here on the public night, where we had, again, 100% cloud, unfortunately, which no doubt contributed to keeping a lot of people awake, because only 53 turned up that night. 10th of June, we had the first Balnarring Joeys and Scouts here, and they were able to see a little bit in the sky. It was mostly cloudy all evening, but 44 of them turned up, and they sort of fed back afterwards that they had an amazing time here. So hopefully they'll be coming back in the future as well. And then 14th of June, last Saturday, we had the special general meeting here, and the outcome of the special general meeting is we decided to change the constitution so we don't have to pay income tax. So that was a bit of a no-brainer really for us, but we had to actually go through the motion of it, and now it's over to the Secretary to get the changes uploaded in time. Coming up soon, this Friday, the Briars has got the winter lantern making from the Echo House here at the Briars. I don't think you need any more telescopes. You think you'll be right? Yep. So they'll be making winter lanterns because it's pretty close to the winter solstice on that date as well. And Phil has arranged for us to show them the night sky if the weather's kind on the evening as well through some of the telescopes here. Then on the Saturday we've got the Working Bee and members barbecue as normal. 24th of June, which I think is a Tuesday, Narrawarren South Cubs. We've given them a viewing night before a couple of years ago, but this is at their new Scout Hall at the same location, but just a brand new building. So that's out at Narrawarren. That won't be here at the Briars, and we're expecting 40 of their Cubs, and it starts at 7 o'clock. Committee meeting is on the Wednesday, 25th of June, over by Zoom. 26th of June, the next night, we've got the Mornington Joeys and Cubs, and I think this one might be multiple groups, might not just be Mornington. Beginning here at the Briars at 6:30. This is the one that Anders Hamilton has arranged for us. And we're only anticipating 30, but you never know on nights like this. 1st of July, the astronaut Chris Hadfield's going to be in Melbourne at Hamer Hall for those who've got tickets to go and see him. Just a reminder that that's coming up. 4th of July, public night here. We're fully booked out. In fact, we're fully booked out for a few months in advance already at the moment, with Trevor giving the talk for that one as well. And then this meeting next month is starts off with the annual general meeting that we have to have, followed by the regular meeting afterwards. And there's no cosmology discovery group here this month, but it's just after the next meeting that the next one comes along.
So Cape Schanck Lighthouse, and it's a really beautiful shot showing the light beams coming out of the lighthouse, and we've got the small and large Magellanic Clouds in the Milky Way there. Unfortunately, this isn't eligible to give Alan recognition for a challenge completed successfully because it's out of bounds on the date. So photos need to be taken during the period of the challenge. So hopefully we'll get another shot from Alan, because obviously he's capable of doing some pretty nice work. Okay, people who completed this challenge were Steve Gerkovich, Pia Pedersen, Phil Holt, Nerida Langcake, Michelle Sykes, Mel Lee, Mark Stevens, Liam Laub, Jamie Pole, Greg Walton, Fred Prater, Dennis Cook, David Rolfe, Chris Kostokanellis and Ben Claringbold. So quite a few there, and the photo that we've got there is of the flower moon being kicked for a goal by Pia Pedersen. So really nice opportunistic photo, walking along, get an iPhone out and grab that shot. So well done, Pia. The flower moon is the moon that occurs in May, and it's called the flower moon because it's during the time of the year in the northern hemisphere where usually the flowers occur, and so it's called the flower moon for that reason. Don't know what we'd call it in the southern hemisphere. Brown leaf moon. Dennis, well done, Dennis. Captured this photo pretty much again the same way, opportunistically, waking up in the middle of the night and seeing the moon rising. So Stairway to the Moon in Marley Point near Sale. And Marley Point is on Lake Wellington in the Gippsland Lake, sort of Golden Beach, Sale area. So a really nice opportunity to get a nice photo there by Dennis, so well done. A few more moonshots coming up. This one was by me, exactly the same thing, smartphone again, on Seaford Beach. And this was about 6.76% illuminated moon. I think Dennis's one before was about 11%, but it still looked bright because of the exposure. This one here during the day still able to pretty nicely make out a very thin crescent. Liam managed these couple of shots, and there's actually these shots here. Liam's taken these with a telescope, a 650 focal length 5-inch Newtonian, which he purchased from John Goodall at the swap meet. That's from your telescope, John. And a DSLR camera, and this is taken from McRae Beach, looking towards Arthur's Seat, about 2 kilometres away. And these shots actually take a fair bit of planning to get done, because you've got to know where the moon's going to rise and where you need to be to line it up with the object that you're targeting. And there's a couple of websites that do this, and Photographer's Ephemeris is one of them. So it's photoephemeris.com, and it lets you line up different targets in different parts of the world with sunrise, moonrise, and different things like that. So yeah, a fair bit of planning that goes into these shots. Next we've got a couple from David Rolfe, and we've got the strawberry moon there. So, sorry? The moon there somewhere. Yeah, the moon. Strawberry moon right there. Is it? That's a fair way in the rough, isn't it? But Dave actually got a couple of these. This one's not the straw. It is the strawberry moon, but it looks pretty plain. But there's actually a filter you can get called a Fragola Luna filter that you clip onto your phone. You get it from Temu for $2. And if we zoom in with the second shot, there we go. Strawberry moon. So well done, Dave. The strawberry moon is called the strawberry moon because it marks the time when the strawberries are ready to harvest. And I think it's a Native American Indian naming where they name it the strawberry moon, because it is the time of year when strawberries are usually ready. The moon doesn't appear any particular colour unless you've got the Fragola filter. But during moonrise, moonset, sunrise, sunset, they do appear a little bit red or orange depending on the conditions of the atmosphere. So there's our strawberry moon. A couple by Fred Prater as well. One of them is eligible, the other one isn't, but so Fred still gets a mention for challenge completed. The one on the right is from January, and we've got Venus setting over Port Phillip Bay, image from Canadian Bay. And you've got Venus, and just above it you can also see Saturn. So we've got Venus there and Saturn there, and this was 18th of January while Fred was trying to image the Comet Atlas at the time. I didn't get a shot of the comet, but he did get that beautiful shot of Venus with the reflections in the water. And the other photo on the left is a couple of red-tailed black cockatoos flying off to Venus. So we've got some real nice colour gradation in the photo. And we've got the cockatoos. Where's my pointer? There it is. And that's Venus up there. So this was on the 25th of May. And a little bit of, boost the colours with a bit of saturation and lower the black point a little bit to get the contrast in that photo. So thank you, Fred. And Ben's got a new toy. This is why we've got getting all the clouds at the moment. Ben's got a drone. And he's managed a couple of really nice shots over the Briars with the drone. This one from the 13th of June, catching the sky over the Port Phillip Bay and the Briars just after sunset. And the next one shows what drones are really, really good for, and that is looking into your neighbour's backyard. So this is our site here at MPAS. This is the school camp, up over the car park, and that's what they've got in their backyard there. Didn't know that. It looks like they've got a gallows set up over here as well. And this is the Eco House with the geodetic dome, and this is where we are sitting right now with our little dome observatory and our other observatory back there, and then we have the nursery over here. So a really nice shot of our home here by Ben, so good stuff. Couple by me, Orion's sword, just coming in amongst the trees over here. So this is just from the backyard. I was setting up with a telescope and noticed that would fall into that spot, so I got the camera out and took that shot. Just with a Canon, it's at 96mm focal length, so I've got to be pretty quick with the shots at that focal length so we don't get the star streaking, so 4 seconds. And the one on the right is taken from here at the Briars, and we've got Scorpius coming up over our observatory here. And this is Scorpius over here with its stars in its tail coming around through there. And then the Milky Way. So that was on 22nd of April, just over here. Nerida got this one here with her Samsung Note 20 Ultra, and this was from Ilford, near Ilford in New South Wales, 24th of May, with a comms tower, and you got the Large Magellanic Cloud in the bottom of the shot there as well. So that's a single shot straight from her smartphone, or Samsung Note, and unedited, so great shot. I'll just point out as well, just to see, we've got the Large Magellanic Cloud down here and Canopus over here, and then these are the 2 pointers pointing to the Southern Cross. So and the Coalsack, yeah, Coalsack Nebula there, and then Eta Carina Nebula there, and yeah, that part of the sky there, so we're very familiar with out here. Mark Stevens managed to get this as well. So same sort of thing, but over the buildings with a smartphone, and he's got Sagittarius over here. So we've got, that's the Ptolemy cluster, I think, shining bright in the middle of the screen. That's the tail of Scorpius through here, Sagittarius through here. The spout of the teapot is just about there, I believe. And coming down through here, we've got Corona Australis, the Southern Crown, or Wan, the boomerang, as it's known by the some indigenous cultures. And then on the left, we've got Aurora, taken from Mark's backyard in Langwarrin, again with a phone. And this was on the day where it was pretty much completely clouded out for most of us, I think. I was trying to get photos of it, but I couldn't see anything through the cloud. But Mark's got this really nice shot with the aurora shining through some thin cloud there, so well done, Mark. Mel went on a little star party with some friends to Ruffy in Victoria. Ruffy's about 150 k's northeast of Melbourne, from what I understand. So a couple of hours drive north. And he managed to get a few photos and a time lapse as well. This is one of Aurora, and another one of the Milky Way, or what is also known as the Emu. So we've got pretty much the head of the Emu up here. That star there would be Alpha Centauri, and then coming back through the body of the Emu, the Milky Way, and it's the Emu's legs down there. Michelle Sykes sent a few in as well. Aurora from her home in Rosebud on the 2nd of June, and these are with an iPhone, and star trails as well. So Michelle sent in a time lapse, which we'll see later on, But when you do collect all of the photos from a time-lapse, you're able to stack them, and she did this with a Lumilapse intervalometer app on her phone and the Star Stacker app, and created that really nice image with the aurora and the star trails. Steve got these two, actually Steve's got a couple of nice shots, these ones here, and I think that's Steve doing star jumps in front of his camera, and some nice, really nice colour in the photos there, and I really like this one by Steve too. So down at Gunnamatta, and we've got some really nice light wispy cloud in front of the aurora, which adds a really, really nice effect to it. So thank you, Steve. Phil, which Peter showed one of Phil's photos earlier, the one on the right, and he also got the one on top. So this was on the 13th of June. And we have some photos by Greg as well, taken here at the observatory. So we've got pretty much the full Milky Way arching over the south elevation of the Briars here. And a couple here showing pretty much every corner of the sky. This was on the PVN, the last PVN. So we've got a photo of the southern sky, which we see, and we've got the large and small Magellanic Clouds in the sky over here. Showing out to the west where everything sets, we've got Sirius, the brightest star in the sky there, and this is the constellation of Canis Major, the big dog. So Sirius is at the chest of the dog. The dog's head would be sort of behind the tree at the moment. Its forelegs are just coming down here, and its hind legs are here with its tail coming out the back there. And then that flows into the constellation Puppis behind that. Northern sky, we've got the beautiful aurora of Melbourne's light pollution in the north, behind our famous tree. And then over to the east as well, we've got the familiar sight that we have at the moment of Scorpius, the scorpion just running through there. And then also a couple of shots of the observatories as well on the 20th of May by Greg. That's our dome, looking through the dome slit, and also our main observatory with all 4 telescopes in view, looking at the Milky Way, and also a line of sight along the large Meade telescope in the observatory as well. So some great photos by Greg. Also we do have a moon dial in front. You might notice a sundial, but there's also a moon dial. So I'm pretty sure that's the moon shadow, isn't it, Greg? On that at the moment, 20th of May, and sorry,
10:15.
10:15, yeah. And our tree with the stars behind it there. So nice shots by Greg. Our contributors board has grown substantially this month. So all of these ones down here, 11111111, these are all first-time contributors to the challenge. So well done to everyone. And I'm hoping next challenge to have to spread this over 2 pages. So we are growing. Okay, our next challenge is MPAS versus Space Telescope. So we're looking at MPAS members' images and comparing them to Hubble and James WST telescope images. This is an example of a photo that Nick Exaris has taken of the Gabriela Mistral Nebula, which is also James WST and Hubble photo as well, of a region that they refer to as the Cosmic Cliffs. But there's a lot of different targets that we're able to compare. Oh, other way. So the criteria for this challenge is that you submit your photo of whatever astronomical object you've taken, and you also compare it to a Hubble or James Webb telescope image of the same object. So make sure, don't make me do all the work, please. Download, get the James Webb or the Hubble image from the NASA website, and I'll tell you where you can get that from in a second, and then compare your photo to the Hubble one. And this works for wide field images as well. So if you've got if you want to grab a wide field shot that you've taken of the sky, and then point out where a couple of different Hubble images maybe were taken on that shot of yours, and then show the Hubble images where they relate to on your image is another way that you can participate in this with a wide field camera as well, not necessarily a telescope. So there's no date criteria on this challenge. You can go through your archives and have a look through old photos and maybe reprocess them, crop them, and compare them to the Space Telescope images. But like I said, please also give me the NASA image that you're comparing to. And also remember to, when you do give the NASA image, to properly credit the image as well. So images from NASA, from Hubble and James WST, pretty much free use images, but do credit where the image is from the NASA website and what the object is. Now, you can go online, and there is actually an ongoing Hubble challenge at the moment. So NASA is running a Hubble challenge. That is the link that I will post on our socials that you can go to. And they do break down the objects that you can image by northern and southern hemisphere objects, and they do also break them down by month. So, where are we? Hang on. Yeah, Brian Stevens actually posted about this on the eScorpius group a couple of months ago. And he does also have the link to this website on his post, but I'll repost it again so you can all have another look at it. So you can pick different objects and just compare your images with the Hubble, and that'll be our next challenge. Now, I do also have a video to show, because there was quite a few. We'll get that off. Okay. There was quite a few time lapses submitted, so I do have a bit of a video to put up, which is a compilation of the time lapses, so bear with me here. This runs for around about 3.5 minutes, and it does have a bit of music to it, so you can entertain yourselves. Where are we? Was there any questions about any of that?
Pretty good, I reckon.
I thought they were pretty good, yeah. I liked that Michelle's time lapse with the star trails. You could see both, because it's pretty much taken east. You could see the stars around the south celestial pole and then also going around to the north as well down there. But you can see that's also on the members' Facebook page, but I'll be posting these up as well so that everyone can have another look at them in their own time too. So, yeah, well done everyone, and we'll see. Oh, yes.
I was wondering about the photographs that were taken with the phone.
Yep.
So do you think they were handheld, sort of literally spontaneously?
Yeah, some of them were, but the long duration ones, you need to rest your phone against something, and then set the delay on the shutter. Because you can't hold your phone for 20 seconds to take a shot, like Nerida's one was about 20 seconds. And also the time lapse was with an iPhone, so that is just set leaning against something, or you can get phone holders with little tripods and let it run on that, but you'd probably need some batteries to do a time lapse to get that going. But yeah, they are leaning. The photo that I took with the moon, that was handheld. Dennis's photo with the moon at the lake was handheld. Mark's photos were handheld with the Aurora and Sagittarius here, so yeah. But the longer exposure ones, you need to lean them on something or get a little tripod for them, yeah. Okay, that's it. Thanks very much.
What can we see in the sky for the rest of June and the first half of July? So this is, again, an image that was the cover image for the Morning Peninsula magazine article this month, the Fighting Dragons of Ara. Just really impressive photo by Nick, as basically all of his images now are just amazing. Okay, quick look at the solar system for the next month or so. So we can see, let me just grab a laser pointer here. So we can see Earth down here, the sun in the middle. And so what that means is that Mars over here is still visible in the evening. Mercury is only visible just around sunset. And Venus is a morning object over here in that part of the sky. And when we zoom out, just now remember that Earth is down here somewhere. And let's zoom out to look at the outer planets as well. What you can see is that Jupiter is basically hiding behind the sun right now, so not visible at all. Saturn is now, well, a morning object or late night object, and Neptune is basically in the same line of sight as Saturn, and Uranus now kind of the same line of sight as Mercury was earlier. Right? So we'll see that in the all sky view in a minute as well. So if we fast forward through the next month now from here, it's actually not that interesting, not that much happening here. Well, we can see that we put a bit more distance between Earth and Mars, and Mercury will now pass between us and the sun at some point, and then also not be visible for a while. But that's for later in July or early August. All right, having a look at what's happening in the next few days. Well, we've got the winter solstice coming up on Saturday. So I just thought I'd add a little video from NASA that is a really nice illustration of what happens at the winter solstice. So if we look at the Earth's axis with its 23.5 degree tilt, it's now pointing directly at the sun for the northern hemisphere. So we've got the sun basically directly overhead at the Tropic of Cancer, which means that at our latitudes in the south, we now have the most kind of shallow angle of the sun for us at the moment, which means we'll have the shortest day of the year for us. Because as you can see, of course, the actual terminator here is just across like this, but since the Earth's axis is tilted, we're taking the long way around through the dark part of the night there. And then from Sunday onwards, obviously the nights are going to get a bit shorter and the days a bit longer again. Okay, let's have a look at the night sky on the 1st of July now. So this is around 5 p.m. We can see Mercury there still in the sky. We have sunset around 10 past 5 now. As I said, the solstice on Saturday, on the 21st of June. Jupiter currently in conjunction with the sun, so hidden from view behind the sun on the 26th of June. Then it'll take a while basically for us to go around the sun enough so that it becomes visible again. Mercury is still an evening object at the moment, and it'll be at its greatest elongation east on the 4th of July. Right? So that'll be quite nice in the sky in the evening just before sunset. And we have the new moon on the 25th of June, then the full moon on the 11th of July, and the new moon again on the 25th of July. So having a look at the night sky just after sunset, we have Mars now setting around 9:30 p.m., but still visible for at least a few hours after sunset, but getting a bit low in the sky. And so we're now around 10 p.m. or so. We can see that the main constellations now, we still have the Southern Cross, but it's already getting a bit lower in the sky. We have Antares pretty much straight overhead. If we look at the actual constellation lines over here, we can see that Scorpius and Sagittarius are still kind of the dominant constellations for the next month. And the Milky Way stretching out all across the sky with the core of the Milky Way right around Sagittarius here. So as you can see, no planets for most of the night, but at least Saturn and Neptune now rising around midnight. Right? So they are coming back into the night, or then later in the year into the evening skies. So Saturn rising around midnight, and Neptune is currently within about 1 degree of Saturn. So that might be an interesting thing to try and image as well, where you could get both of them in the same field of view. Venus is a very bright morning object at the moment, and Uranus is quite close to Venus, so rising just a few minutes after Venus. And we have sunrise around 7:35 on the 1st of July. Quick look at the apparent sizes of the planets. Again, probably not that interesting because a lot of them are not that easily observable. But we can see Mars getting pretty small, Uranus and Neptune, basically just the tiny blue disks, they are almost all the time. And Jupiter is behind the sun at the moment. So that's also why the apparent size is pretty small. It's, if we could look straight through the sun, that's the size it would appear at. But it's also basically as far away as possible as it could be, and therefore quite small. Saturn, as now an early morning object, should be quite easily observable and still a reasonable size at the moment. Same as last month and the month before and the month before that. We don't have any interesting comets in the sky at the moment. And we have 2 meteor showers towards the end of July, so not really for the next 4 weeks or so, but I thought I'd just put them up already, because at least the first one is starting around the middle of July, but peaking towards the end of July. So maybe it's something to talk about for the next meeting. And then the Alpha Capricornids also starting in early July, but peaking at the end of July. And I think for both of them, we actually won't have, they're both peaking around the 30th, and we shouldn't have any interference from the moon around that time. And that's all. Sources, as always, Stellarium, NASA, Eyes on the Solar System, and the Astronomy Almanac. Any questions?
What time of the year, Guido, just ballpark figure, can we see Saturn like about 9 o'clock like here?
I didn't. So the question was when Saturn will be back in the sky around 9 o'clock or so. So I guess probably about 3 months from now. I haven't actually checked it, but yeah. So towards the end of the year, but I mean, obviously we are catching up now, right? So it'll rise a bit earlier every month from now. Yeah. Yeah.
Notice Mercury is looking bigger than Mars.
Oh, so the apparent size, Mercury looking bigger than Mars. Yes, we are moving away from Mars now, right? So, and Mercury will be at its greatest elongation east, which is not the closest point to us because that's when it's between us and the sun, so we can't see it. But yeah, that's actually interesting, right? Because it's obviously quite a bit smaller than Mars, but it is.
Closest planet to us, closest to us.
It's also, okay, so Mark's saying that Mercury is the closest planet to us on average, closer than Venus.
I think we've been going, Venus runs away from us, and Mercury catches us. So
so maybe this.
Yeah, but as Venus moves further around its orbit, Mercury will get there and closer to Earth.
Yeah, exactly. So this is on the 18th of June, but you could see later on, it was actually, maybe I'll just quickly fast forward through the, I'm not sure that's working. Right, so you can see here, can I pause this? You can see we are actually moving away from Mars at the moment, right? Because we are traveling faster than Mars on its orbit further out, and Mercury is catching up to us. And so this is around the 4th of July, so yeah, similar to when the apparent size comparison was. And so we are quite a bit closer to Mercury than to Mars at this point.
Elongation, 4th of July.
So
yeah.
Everyone goes on the chaser and they ask what's the closest planet to Earth, because they get it so big.
Yes. All right, any other questions? All right, thanks.
Well, on to the sun. This is Professor Chris Lintott from Gresham College in London. I was quite surprised to find that Gresham College has been around for over 400 years. So it's been around a very long time in London, and he's one of their astronomers. He's also Professor of Astrophysics at the University of Oxford and Research Fellow at New College. He's the founder, if any of you have ever done any of the citizen science online things on your computer, he's the founder of the one called Zooniverse, and that has 2 million volunteers online doing various scientific research, assisting professional astronomers and other scientists as well. So this public lecture is courtesy of Gresham College, and it was recorded a couple of months ago in London, and goes for just under an hour. So if during that time you wish to get up and have a cup of coffee, please do so, or a cup of tea.
Please welcome Professor Chris Lintott.
Evening, everybody. Thank you very much for being here. I thought this was a good subject for a cold January day, and I'm delighted to see that so many of you agree. This has been the most difficult lecture I've written of my tenure at Gresham so far, because the sun is so familiar to all of us. Wherever humankind has gone, wherever we've been in the world or indeed in the solar system, we have the sun as our constant presence. And so it's a subject that you perhaps feel you know all about. This is a gratuitous sunset photo taken on Mars by one of the Mars rovers from Spirit, the robot geologist that explored the red planet on May the 19th, 2005, showing sunset on the planet. But it's that familiar scene, rendered Earth-like by the presence of our friendly neighborhood star. It gives us the sky that we're used to. The blue color in this image is pretty close to what you would have seen if you were sitting on Mars next to the rover. Do take your own oxygen, of course. And it's striking how universal an understanding of the sun as an important and friendly presence is. Even in kids' drawings, this masterpiece by my nephew Finn, for example, shows a dramatic scene. He calls it the end of the dinosaurs. I think a volcano is involved. But despite the devastation on Earth, in the top left, a nice friendly yellow disk with rays coming out of it, how we all think about the sun, though I guess sometimes it has sunglasses on as well. Fred Hoyle, the great cosmologist, and the person who taught us how many of the stars in the universe shine, once started a lecture on stellar, not solar, but stellar structure in Cambridge by noting that stars are simple. And a heckler from the back of the room said, "If you were that far away, you'd look simple too, Fred." And one of the problems that I have approaching the sun as an astrophysicist is that it's close enough that we can see that it's complicated. When stars are distant, when they're just a point of light in the night sky, then it's easy to think of them as simple. But when we can see the sun close up, we get a long way from the picture that we're used to drawing as kids. The lecture is particularly timely because of the adventures of a small space probe shown here in this artist's impression, the Parker Solar Probe, which has just fulfilled an ambition that goes back to the dawning of the space age. One of the 3 tasks that were set to NASA when it was set up in the late 1950s was to send a craft close to the sun to understand the processes that drive our star. This was so complicated that it's only been achieved in the last few weeks. The Parker Solar Probe flew closer than any other object ever has to the solar surface. If the sun and the Earth were a meter apart, then the closest approach would have been about 4 centimeters. And the probe, as it passed just 3.8 million miles above the visible surface of the star, was moving at 430,000 miles per hour, making it the fastest human-made object ever. It's a remarkable technological achievement. The temperature on the front of the probe was about 1,000 degrees centigrade, and the reason it took NASA 70 years to get to this technology was that a heat shield needed to be developed so that the instruments work at pretty much room temperature, despite the presence of the sun just on the other side of them. So this lecture includes some of the latest results from Parker, but also from a whole suite of missions which carpet the solar system and which help us understand what's happening on our nearest star. There are many examples here, and I won't go through them all, but what I really want to point out is that pretty much any spacecraft in operation is doing some sort of solar sensing. There's an example given here in the bottom right of the latest Mars rover, Curiosity, which has a radiation instrument to monitor the effect of solar weather on the red planet. And I'll come back right at the end of the talk to the contributions of the Voyager probes, initially launched to explore the giant planets of the solar system, but now out in interstellar space, giving us the other end of the story from Parker. This is the only time, I suspect, in our lifetimes where we'll be receiving data both from a spacecraft that's skimming through the atmosphere of the sun and from spacecraft that are out on the edge of the solar system. And combining those two things tells us a story that affects us sitting in the middle on Earth. The other spacecraft I want to make sure that I mention right up at the top is a European contribution to this fleet. It's a spacecraft called Solar Orbiter, which sits a little further out than Parker. It's on a 6-month elliptical orbit, so it swings closer and further away from the sun. And its role is essentially to monitor the whole disk. So this is a few months worth, actually about a year's worth of solar orbiter images in the ultraviolet that shows an active sun with details that we'll get into. And the blue flashes here are flares, material that's flung off out into the solar system. And you can see the detail in these images when combined with the instruments from Parker's remarkable passage close to the sun are giving us a new picture of this star. But we should go back to basics. We should talk about the things that everyone knows about the sun. And I have to say, I started trying to write this lecture right at the end of last year, as I was sort of reaching Christmas burnout around the time when term had finished, and I was pretty overwhelmed. And I sat with a piece of paper for an hour trying to think about what I wanted to tell you about the sun. And maybe I'll just show you those notes, because I think they capture where I got to. You see, this is what people know about the sun. So it is true that the sun is massive. I get paid for this lecture. It is true that the sun is massive. Now, how we know that is interesting. It's calculated by an understanding of orbital mechanics, of watching the planets go round the sun, enables you to calculate this number, the mass of the sun. But you do need to know the distance to the sun. And that was first calculated with precision in the 18th century when astronomers watched the transit of Venus, when they watched the planet Venus pass in front of the sun from different places on the Earth and used parallax, the difference in timings of that event from different places to work out a distance, plug that into the maths via a method originally suggested by Edmund Halley and others, and you end up with the idea that the sun weighs about 333,000 times the mass of the Earth. So that's about 2 times 10 to the 30, so 1,000 billion kilograms. It's massive. Tick, first thing achieved. It's also big, I guess, I should say that. It's about 1.3 million Earths by volume and about 109 across the front. Hot is rather more controversial, which sounds ridiculous. Surely the one thing we know is that the sun is hot, but the great William Herschel, the greatest English observer of all time, the discoverer of Uranus, in the 18th century was a proponent of the idea that the sun was cold. In fact, he described it as a cool, dark, solid globe, clothed in luxuriant vegetation, doubtlessly richly stored with inhabitants, so he thought people lived on the sun, and he said, look, if the argument's this, so he's actually got this model, so here we go, so you have a dark Earth-like globe, then you have a planetary clouds which block our view of what are presumably cities and civilizations on the surface of the sun, and then there's a luminous shell above that which we see. And this sounds ridiculous, but his argument was, look, if it was just light that caused heat, if the fact that this was luminous meant it was hot, then surely the tops of mountains which are closer to the sun would be warm rather than snow-covered. And so he argued that you need what he called a calorific medium, something on the ground that converts light to heat. And in the absence of that, surely people could live on the sun. Now, I'm here to declare that this is actually our modern... No, not really. We no longer believe that the sun is inhabited. We know that it's hot, and people quickly realized in the 18th century that, indeed, the light from the sun indicates that it's hot, about 6,000 degrees on the visible surface. But that opened up the argument of where the source of the energy that the sun provides is coming from. It was a problem that troubled a large number of physicists, many of which looked slightly like walruses. This is Kelvin and this is Helmholtz, two of the people engaged in this. Kelvin, probably the great 19th century physicist. They argued that the sun really had to get its source of energy internally. That what was happening was that material that made up the sun, either primordial material that had been assembled somehow into this star, or material that was still raining down onto the sun, comets, meteors, and so on, that the contraction of that material, squeezed under gravity, would release heat. Kelvin said that some form of this theory is certainly the true and complete explanation of solar heat, and this can scarcely be doubted when the following reasons are considered. One, no other natural explanation can be conceived. All right, well, that's cheating. Two, the chemical theory, the idea that the sun is made of coal or something like that, is quite insufficient because the most energetic chemical action that we know taking place between substances amounting to the whole sun's mass, so this is if the sun was made of coal or something like that, would generate 3,000 years heat. And they knew that the Earth was older than 3,000 years. And he goes on and says, there's no difficulty in counting for 20 million years worth of heat by the meteoric theory, by this collapse. And you can actually work out, we know the mass of the sun, you can work out what's called the Kelvin-Helmholtz timescale, you can work out how long that body would take to collapse, and you get a value in sort of tens of millions of years. So you can explain a solar system that's tens of millions of years old just by having things collapse. And you can extend it a bit by throwing more stuff in, and indeed today, using satellites like SOHO, with the sun's disk blocked out here, we see comets plunging into the sun. That's a comet on the right there, and about 4,000 or 5,000 of these things have been seen in the last 20 years. So stuff does fall in. You still can't quite beat a few tens of millions of years. And this is a problem, because of observations made by people like geologist James Hutton of places like this. This is Sicker Point in Scotland. This is a place where two different types of rock rub up against each other. In fact, you can see in this sketch made in 1788 from James Hall, the crucial observation. You've got these vertical rocks. These are grey wacke sandstone, very suitable for growing Sauvignon Blanc on, but probably not in Scotland. But importantly, deposited over many millions of years, possibly at the base of an ocean. We now know they're about 435 million years old. But they're topped by these rocks with a different angle of spread. Those are the red ones on the top there. This is an old red sandstone. It's 360 million years ago old. And in between, there's 65 million years of missing history. And Hutton knew that here and in other places, he was looking at two slow processes with an unknown gap in between them. And he used things like this to argue for the concept of deep time. Though he wouldn't have known the numbers that I told you, he realized that the Earth had to be hundreds of millions or even billions of years old. And so a theory of the sun's heat, which could only account for a sun that maybe was 20 or 30 million years ago, was incompatible with geology, with a growing understanding of how old the Earth was. This was not a view accepted by Kelvin, and a controversy about whether the Earth truly was old or whether the sun needed a different power source rumbled on for most of the 19th century until it was realized that there was another potential source. Radioactivity was discovered in the lab. Materials that when they break down under nuclear fission emit heat were discovered, so if you make the sun of those, you can have a long-lived radioactive sun. So this means the crucial question becomes, what is the sun made of? And unbelievably, we can actually measure that directly. This is a modern picture of the solar spectrum, of the light of the sun split into its constituent wavelengths. You can see immediately two features. One is that there's a rainbow, and here I've wrapped the rainbow round so that it is not just one long strip, but you go from top to bottom. But second, that there are these dark patches, and both of these things are important. Now, the solar rainbow was known since Newton's time. Newton did experiments like that described in this rather charming diagram that showed in 1672 that if you passed light through a prism, it splits into a rainbow. What appears to be bright white sunlight is actually made up of all the colors combined. But in the early 19th century, a German scientist called Fraunhofer made the discovery of these dark lines. They're still called Fraunhofer lines. Fraunhofer, by the way, if you ever get a chance, read up on his biography. It's an extraordinary life. He was orphaned at the age of 11, apprenticed to a glassmaker who treated him appallingly, and then the shop that he was working in collapsed, and the young Fraunhofer happened to be rescued by a passing prince who got talking to him and funded his scientific education as a result, forcing his employer to provide both books and time to study, thus leading to one of the great scientific careers, which was then cut short at the age of 39 because of exposure to heavy metals from his glassmaking. But in between, he discovered these dark lines in the solar spectrum. And the explanation for these we now know, since Kirchhoff and Bunsen and others in the 19th century, is that these are the fingerprints of different elements in the solar spectrum. So the way this works is you have a source of light, of all colors of light. Let's just take it as read that the sun's that for now. That would produce a continuous rainbow, like in the bottom left. If you have a cloud of gas, emission from gaseous molecules would produce a series of bright lines, and the position of these lines tells you which elements exist in the gas. This is a process to do with the capture and escape of electrons in different species that correspond to different energies. If you're looking at a cloud of gas in front of a bright source, then you end up with this absorption spectra, with these dark lines as we see in the sun. So what we're seeing in Fraunhofer's observations is the effect of the solar atmosphere on the light that's coming from the bright surface of the sun. A race was on to try and identify which lines corresponded to which elements. Most famously, people like Norman Lockyer, working in first Kensington and then in Devon, discovered that some of these lines appeared to belong to a new element, to helium, named after Helios, the sun god, but also that the sun seemed almost overwhelmingly to be made of hydrogen. And so our radioactive theory, the idea that you could power the sun with heavy elements, disappears. There isn't enough heavy stuff in the uranium, or not much uranium, etc., in the sun to provide a heat source. And so this mystery of what the sun's power source actually was persisted into the 20th century. Now, I should say it was understood that the sun was hot. We've established that already. And that makes things slightly simpler when we're thinking about the structure of the sun. Now, I can quote, for example, contemporary philosophers, they might be giants, who sang, as many of you will know, that the sun is a mass of incandescent gas. And this is not true. The sun is at a high enough temperature that its atoms have lost their electrons. And so the sun exists not as a gas, but as a plasma, where you have atomic nuclei and then free-floating electrons. And to be fair to the band They Might Be Giants, I should point out they have re-recorded, I'm delighted to have discovered in preparing this lecture, a new version of their song, which begins, "The sun is a miasma of incandescent plasma," which I'm sure we can all agree is an improvement. So, we have a hot sun made of atomic nuclei with a sea of electrons. In 1926, in 1920, Eddington, who we met in last time's black hole lecture, realized that nuclear fusion could be the answer. That if you took 4 hydrogen atoms and fused them together, you can produce a single helium atom. And it was newly discovered in the 1920s that the weight of one helium atom is a tiny percentage smaller than the weight of 4 hydrogen atoms. And because of that difference, when you fuse 4 hydrogen atoms together to form 1 helium, you get, via E equals mc squared, Einstein's great equation, a release of energy. And so Eddington realized that the sun could be burning hydrogen to helium. And indeed, that's what's happening at its core at temperatures of millions of degrees. There's a cycle of reactions happening, the most common of which is known as the proton-proton-1 cycle, which is shown here. You take 2 protons, 2 hydrogen nuclei, they merge, they produce a deuterium nucleus with 1 proton and 1 neutron. That then merges with another proton, you form a helium nucleus with 2 protons and a neutron, and then you merge 2 of those together and you get your final stable form of helium and 2 hydrogens. This is not a fast process. It's very sensitive to temperature, actually proportional to T to the 12, so a small change in temperature will make a big difference. And the average proton in the center of the sun will hang around for about 9 billion years before it takes part in this reaction. It's that first step that's limiting, and as a result, the lifetime of the sun is of order 8 to 10 billion years. Once you form your deuterium that goes fast. That will merge within about a second, and then about 400 years for the helium-3 to form stable helium-4. And there are other more complicated reactions that are going on as well. I should say, by the way, that it's been argued by my predecessor in this chair, John Barrow, and others, that we're lucky that the universe does this. You can imagine a world in which helium-2, in other words, a nucleus of just 2 protons, is stable, so that you could have a much simpler process by which 2 protons come together directly, form helium-2, and the process stops. In our universe, that nucleus isn't stable, and it would split back out into 2 protons. But if it were, then stars would very quickly produce a lot of helium-2, and you'd burn through their fuel almost instantly in the matter of a few million years. And that would mean that there'd be no long-lived stars, and hence presumably no planets with life on in the universe. So this is often used as an argument that we live in a universe where we should pay attention to the anthropic principle, the idea that the universe is the way it is because we're here to see it. We don't live in that universe, we have this proton-proton cycle, and it would be nice to know that this complicated chain of reactions is actually what's going on. And luckily we get some direct evidence for this. One of the byproducts of that first reaction, the combination of 2 protons, is a small particle called a neutrino. Now neutrinos don't interact with their surroundings very easily at all. John Updike, the poet, wrote a poem about neutrinos, and he said, "The Earth is just a silly ball to them through which they simply pass." They also simply pass through the rest of the structure of the sun. They escape from the sun pretty quickly, and seen here is the Super Kamiokande detector in Japan, a giant tank made of water surrounded by photomultiplier tubes with a bunch of physicists in a rubber boat slowly inspecting their instrument in this case, which can detect the passage of these neutrinos. And we now know that we get the predicted number of neutrinos from the sun as we'd expect from this proton-proton cycle. There was a controversy for a while because we didn't see enough, but we now know that neutrinos can undergo a change on the way from the sun. If we take that into account, we can see direct evidence that the proton-proton cycle is happening. As important is the fact that those early reactions, and indeed several other steps, produce light at the center of the sun. And that radiation spreads out from the center of the star. But one of the more astounding facts is that we don't see it instantly. We're used to thinking of light moving quickly. But if you're outside today, the sunlight that you were enjoying left the center of the sun about 170,000 years ago, about the same time that the first Homo sapiens were congratulating themselves for inventing clothing, to give you a scale. What happens is, because of the density of the sun, any photon emitted at the core will quickly encounter another proton, be absorbed and then re-emitted. And so they bounce around in essentially a random walk. This is one simulated example of the path taken by a photon in escaping the sun. So until they reach the surface, they disappear. They take this very long and convoluted process. They then take 8 minutes to get to us from the sun traveling through free space. The picture's complicated again. We actually have a core, a radiative zone where these photons are able to move outwards, and then there's a convective zone at the top, an area where there are large circulations of material rising and falling in the outer layers of the sun, rather like the circulation of Earth in the great air currents that we see in our atmosphere. We know about this structure because colleagues have made a detailed study of the vibrations of the surface of the sun, a science called helioseismology, which seems to delight in wonderful names for experiments. There's GONG, the Global Oscillations Network Group. Trying quite hard there to make that work. And my favorite, our local helioseismologists, Bison, the Birmingham Solar Oscillations Network. And they've done an enormous amount of work, the equivalent of using earthquakes to understand the Earth's core. We look at vibrations on the surface of the sun to understand the internal structure. The core is mysterious. The rest of it has begun to make sense. So we have this surface, we have this continuous spectrum. It's an interesting problem, by the way, why the sun emits a broad brush spectrum, a continuous spectrum. I don't have time to talk about it, but when we look at that visible surface, that area from which photons escape, when we look in detail, then we see a remarkably complicated picture. This is an image from the Daniel K. Inouye Solar Telescope in Hawaii. Each cell that you see here is the size of Texas, and I'm going to take 10 minutes of observation, speed them up for you. And what you're seeing here is a dynamic surface of the sun. This isn't a computer simulation. These are real images from the largest telescope in the world that studies the sun. And what you can see is a changing pattern of what are known as granules, these cell-like structures which swell and shrink, which turn over and represent the upper surface of that convective zone, that region where material's bubbling up to the surface. If I play that again, you can see in between the granules, there are really fine scale structures. The smallest features in this image are only about 30 kilometers across, and those bright patches are going to turn out to be very important. But even here, with this first close-up image of the sun, we've come a long way from a bright yellow disk in the sky. We've reached a complicated and difficult place to explain. Let's zoom out a bit. Here's the sun as it was yesterday, seen by the Solar Dynamical Observatory, and this is an ultraviolet image, so you can see on the surface of the sun, bright patches here are hot, so there are areas of intense activity. We've got these strange streamers that are twisted around. There's this large dark region across the center, a cooler region on the surface of the sun. But if we step through different wavelengths of light, if we use different cameras, the picture changes. So you can see here, in the extreme ultraviolet, you can see that there is activity. That dark area has become a site of one large structure. We can see in this image there are filaments and prominences on the edge of the sun, large loops, each of which is big enough to contain the Earth. And in excited X-rays, we see that those areas where materials shooting up into the sun are extremely hot indeed, going up to a few million degrees. I recommend, by the way, the Solar Dynamic Observatory updates its images about 3 or 4 times a day, and I really recommend starting your day by seeing what the sun's doing. It's a nice way to feel part of the universe. You don't even need these fancy cameras. This is from SDO, again from yesterday, but this is a visible light image of the sun. And in some ways, this is the oldest sort of solar observing. What you can see here is the yellow disk that we're expecting, but there are also a couple of dark sunspot groups on the sun at the minute. And these have been observed from before telescopic times, when people occasionally were able to look at the sun through thick fog. Do not try and look at the sun directly. It's dangerous. You will blind yourself if you try and use optical aid to do that. But early telescopic observers, Galileo and Thomas Harriot, the first person in the UK, we think, to make scientific instruments, observations with a telescope, in 1610, spotted sunspots. I should say Thomas Harriot, if you don't know the Harriot story, he's great. He got hold of what he called a Dutch trunk, which turns out to have been a telescope. He drew the first map of the moon, and I was talking to somebody about him yesterday, and found out that he's credited with the introduction of the potato to the UK. So the first astronomer and the person who invented chips, he should be a national hero, I think. Anyway, I'm not going to show you these are Galileo's observations of sunspots. He did actually damage his eyes by making these, but this is a modern animation. And what you can see is that over the course of several days, this is about a month's worth of observations of the sun made at about the same time each day, the spots move across the surface, and they also change and evolve as they do. So by watching sunspots like this, observers were able to deduce that the sun rotates, but it has a rotation period that depends on where you are. It's about 24.5 days near the equator, about 36 days near the poles. So there's what we call a differential rotation. Remember, this isn't a solid body. It's a miasma of incandescent plasma. It is a rotating body of gas, if you prefer. So what's going on? What are these sunspots? Well, they're produced by the magnetic field of the sun. And we're used to the idea of magnetic fields. If you remember your geography at school, you'll know that we think of the Earth as having the kind of field that you associate with a bar magnet, with poles and then these looping field lines. And that's a pretty good first description of the solar field, except that the entire sun is rotating. And so that means that once every 8 months, the field lines get completely wrapped around the sun, doubling the strength of the field. And so you end up with a twisted magnetic field. There's also all that motion I told you about in the upper layers of the solar atmosphere. And that causes twisting in the field. And you can think of this as twisting up elastic bands. So you're storing energy within the magnetic field. And that stored energy, and its need to escape, creates a range of behavior, including sunspots. So here are some more examples from that telescope on Maui in Hawaii. They show the complexity of the quiet sun in the top right and the bottom left, where there are these dark threads visible. But the other images here are all sunspots. Here is a particularly lovely example. The dark region is cooler. Because it's cooler, light is escaping from the solar surface lower down. So this is a place where we're seeing down into the sun. You can see the dark umbra, the central shadow, surrounded by the brighter penumbra, which has these filaments. And on the left here, these are decaying sunspots. We're watching the end of one of these sunspots. This is a place where magnetic field lines are escaping out of the sun and they're causing material to flow. Early observers realized that these sunspots and other markers of solar activity follow a cycle. Here's an annual survey of the state of the sun, running from 1996 to 2020, from the long-lived SOHO probe that the European Space Agency and NASA collaborated on. And what you can see is that we start off in 96 with a quiet sun, it becomes more active, it returns to being quiet, and then it repeats again. And there's a roughly 11-year cycle here. More remarkably, if you plot the positions of sunspots each day on a graph, you get what's called the butterfly diagram. So not only does activity come and go, it moves across the surface of the sun. You start each cycle with sunspots far from the equator. Over time, over the 11 years, they move closer to the center. And over time, then the sunspots of the next cycle will appear. So one can measure out your life in solar cycles. We count from the first cycle that was observed in 1755. We're currently in cycle 25. I guess I was born at the tail end of 20, went to school during cycle 21, university 22, and have been thinking about astronomy for most of cycle 23 and 24. But you can also see from this graph at the bottom here, and this is just the area of the sun that's covered with a sunspot, you see there are obviously longer-term trends here as well. That each cycle isn't the same. And it's possible that we've lived through a period of intense solar activity that's now fading. That we expect the current cycle, 24 was very puny, 25 is at its maximum now, but does not appear to be back to, say, the heights that we saw in the 50s or 60s. And it's possible we're entering a period where there'll be very little solar activity. Now, I should say that's not enough to allow us to get away with climate change. A change in temperature might be as much as a fraction of a degree because of this change, but it shows us that there's a complex long-term evolution of the sun going on, that each cycle affects its subsequent neighbors and so on. And the origins of this 11-year cycle are still being debated today. We actually think it's a 22-year cycle because the polarity, the north and south pole, flip in between each cycle. But we should continue on outwards. We reach the solar surface and sunspots. We can go further. We can look at the solar corona, its atmosphere, seen here during a total solar eclipse. During such an event, the moon blocks out the bright photosphere of the sun, and we're left with a momentary glimpse lasting just a few minutes of the pearly white corona of the sun. You can see here there's also a few prominences around on the right-hand side, those places where material's being thrown up above the solar surface, shown here in red. Now, if you haven't seen an eclipse, I want to pause the lecture briefly to recommend that you do. I couldn't think of a way to be persuasive other than to show you the effect of an eclipse. And so this is me about 3 minutes after I'd lived through totality in Farmersville, Ohio, back in April. Every time I try and tell people what an eclipse is like, what a total eclipse is like, and there are no words for it. I cried. It was beautiful. There were prominences. There's a prominence, a bright orange glow at the bottom of the sun. Beautiful corona, long streamers, a solar maximum corona, all of which makes sense scientifically, but my God, we're so lucky to live on a planet. There's more, and I had a Bloody Mary, but I sincerely recommend it. It's one of life's great experiences. The next time in the UK is September 2030. You can go to the Channel Islands in 2081, but if you do get a chance to travel, do get yourself into a total eclipse. Now, that reaction is one of the reasons I can't be a solar physicist, because solar physicists like to make their measurements of their corona during eclipses, and they've taught us, for example, that the shape of the corona changes. This is 1994's total eclipse versus 1980. 1994 was a solar minimum, very little solar activity. We've got these long streamers. 1980, a solar maximum, we have a much more symmetrical corona. So the atmosphere is responsive to what's happening underneath. Solar physicists are impatient. They don't like to wait for eclipses, and so people have used a variety of methods to try and study the corona the rest of the time. The early attempts involved putting telescopes on early sounding rockets, flying them under balloons, or in one of my favorite inventions, a thing called a rockoon, which is what happens when you put a rocket underneath a balloon and then wait to launch it until the time is right. The idea here was to catch the sun being active. So they would fly a high altitude balloon with a rocket, wait for the sun to do something interesting, and then blast the rocket in space to take quick observations, usually going straight through the balloon itself as well, causing all sorts of interesting landfall. Results from slightly MacGyverish experiments like this taught us that the corona is hot. It's actually hotter than the surface of the sun. It's millions of degrees. And we can study it now with coronagraphs. This is a satellite in space, SOHO, that's blocked out the sun so you can see the outer corona. But understanding how you resolve this paradox of an outer atmosphere that's hotter than the surface of the body that's heating it took a long while. It required specialized spacecraft, some of which sent back spectacular images. This is a video from the TRACE spacecraft, which was sent up to look at the corona and particularly how it relates to the surface of the sun. This is a video from 1998. We can zoom in and you can see the complexity of what's going on the surface here. These streamers link up from the surface of the sun into the atmosphere, and they must carry magnetic flux and material up into the corona. But the details, to the frustration of physicists, weren't available from images like this. They look fantastic. I had trace imagery as my computer background for a long time, but it's only when we got back to these images, taken in the last few years, that show those 30-kilometer size features that people could see what's going on. If you look, there are bright patches in between the cells, in between the granules. And those bright patches are places where material is connecting back up to the corona. So it's the structure of the sun in between these active regions that's heating up its outer atmosphere and maintaining a corona at millions of degrees. Now, that corona stretches out into space. It can have a dramatic effect on its surroundings. This is an image from a spacecraft called Stereo. Stereo was actually a mission with two probes, one which went ahead of the Earth and one which went behind the Earth, and which looked back at the space between the sun, which is off to the right of this image near the grasshopper, and the left. And you can see in a movie over the course of one day, material flowing outwards from the corona. And the thing coming inwards is poor Comet Encke, a periodic comet which you can see is disrupted. Its tail acts like a windsock in the face of this solar wind. And you can actually see somewhere about a third of the way through the video, the tail disconnects there and disappears out, carried out to the outer solar system. The comet perseveres bravely. On Earth, we experience an interaction with the sun when we see the northern lights. We had a couple of amazing displays last year. This is from October, taken just down the road from my home in Oxford, showing a beautiful display of the aurora caused by particles from the solar wind hitting our planet's atmosphere, being funneled by its magnetic field down to the upper atmosphere and exciting atoms in our atmosphere to glow. But understanding where that solar wind comes from is again a big problem. This is why solar physicists wanted to get as close to the sun as Parker did. For the first time, the Parker Solar Probe is flying close enough to the sun to be in the region where the particles that form this solar wind are accelerated. So we're actually studying the processes which speed up this wind that spreads out into the solar system. And sometimes we've been able to combine those results with more distant views. So this is a view of the sun from March in 2022. And at this time, Parker was close to the sun, so we had a sense of what was going on low down in the solar wind. The dotted line here represents the solar orbiter trajectory, so we got this view of what was happening down on the surface. And if you imagine being able to put together an instrument that's collecting and analyzing the particles that are flowing from the sun with this detailed view, you can see why scientists are now confident that we understand where the solar wind is coming from. It's from this complex and magnetic interaction around the active regions on the sun, not from the activity that we see itself, but from its effects on the rest of the sun. Solar activity can be more dramatic. This is the 1860 eclipse. This is a beautiful drawing of the corona, but it appears to me that the observer has dropped a cinnamon roll or something onto their telescope. This feature down in the bottom right, which appears in all contemporary descriptions of this one particular eclipse in 1860, is what we would call a coronal mass ejection. This is a modern version of that from Soho. And a CME is a mountain's worth of material shed quickly from the sun and sent flooding across the solar system. My friend Chris Scott, who studies the sun and its effects on our upper atmosphere, talks about it as a billion tons of matter moving at 1 million miles an hour across the solar system. And these things slam into our atmosphere and cause spectacular auroral displays. The most exciting of those came just a year before that 1860 eclipse. It's known as the Carrington event, after the observer in the UK, in fact in Surrey, this is the rather wonderful Red Hill Observatory, a nice bucolic house with a dome stuck on the end, every astronomer's dream home. This is Richard Carrington, who made, in 1859, a drawing on the 1st of September of this extremely large and complicated sunspot group on the surface of the sun. And Carrington noticed while he was observing that there was a flash of light that was brighter than anything he'd seen. And what he'd seen was one of these coronal mass ejections, we think, shooting up from this sunspot group. 24 hours later, magnetic observatories in Greenwich and elsewhere recorded a disturbance in the Earth's magnetic field, and an enormous auroral storm was seen more or less right across the planet. There's a wonderful description, for example, from a gold miner in Perth in Australia. Now, that's pretty close to the equator. We don't normally get the southern lights there, but the record records that a scene of almost unspeakable beauty presented itself. Lights of every imaginable color issued from the southern heavens, with one color fading away, only to give place to another, if possible more beautiful than the last. The streams mounting to the zenith, but always becoming a rich purple when reaching there. The rationalist and the pantheist saw nature in her most exquisite robes, recognizing the divine immanence, immutable law, cause and effect. The superstitious and the fanatical had dire forebodings and thought it a foreshadowing of Armageddon and final dissolution. This is the kind of scientific description we deserve, I think, for these kind of events. The point is, it was spectacular. There's a wonderful record of telegraph operators in the US discovering that they could operate their systems without any power source. They unplugged their batteries and found they could still communicate across the continent because of the electrical current provided by the aurora. Mostly, they talked about how strange this was. We have the records. These days, this kind of storm may cause enormous economic damage to an economy that's used to communication and electronics and spaceborne technology, but it was our first realization that these CMEs could have a serious effect on Earth. And they're still the subject of continuing study. I want to mention briefly, for example, work by Jenny O'Kane at University College London's Mullard Space Science Laboratory, where she's been looking at stealth coronal mass ejections. You can see one here in this image, but using Solar Orbiter and Parker, finding these things coming from the quiet bits of the sun, but still packing a magnetic punch capable of affecting what we're seeing on Earth. When places like the Met Office make predictions of solar weather, they have to worry about these sort of things as well. And the further you get and the deeper you get into the literature, the more you realize that A, solar physicists are having fun, and B, these things are complicated. There's been great excitement, and these are real images stitched together. These are from Solar Orbiter, though they're showing a feature that Parker also sees of a switchback. So you can see this is a streamer coming out from the corona, and hopefully you can see there's a kind of S shape there. So normal theory would suggest that these things should just stream out, but that we keep seeing these changes. And it's to do with the twisting and alteration of the magnetic field of the sun in ways that we're only now beginning to understand from these missions. And I realize as I'm talking like this that we've come a long way from my piece of paper that said the sun was massive and hot. You realize that to understand the sun, because we have the ability to study it in detail, you have this complex magneto-hydrodynamical puzzle that requires equations and computer simulations and sophisticated technology just to answer the question, what will the sun be like tomorrow? Let alone what will the sun be like in a decade or 100 or 1,000 years' time. It is a complicated system worth studying. And just in the last month, there's been the release of what's called the Decadal Study in the US. This is a National Academy report that reviewed all of heliospheric science and said what we should do in the future to study the sun. And they proposed a couple of missions, one called Lynx, which would have 6 spacecraft in Earth orbit, swinging out to 9 times the radius of the Earth to understand this interaction between the Earth and Sun. But they're also proposing a polar orbiter to go for only the second time. You send a spacecraft out to Jupiter, you swing around Jupiter, and you swing up and over the poles of the sun, a region that we've studied once and have no pictures of, but which is crucial in understanding these magnetic interactions. One final question is that given that we can study the sun because it's close, it's important, I think, to think about whether the things that we see here must also happen on other stars. After all, we know the sun is special because it has us going around it. And so it may be that the sun has phenomena that we don't see elsewhere. We've seen star spots on other stars, mostly on large stars where we're able to resolve them. But one particular exciting line of inquiry that I think is fascinating and will be important in the next couple of years is the search for solar siblings, for stars that formed 5 billion years ago in the same nebula, the same nursery as our own sun. We found one good one so far. It's called HD 162826. It's here in the sky, just in the summer sky from the UK. And we know it's our sibling based on how it's moving through the galaxy and also the amount of rare elements like barium that it's got in its atmosphere that matches the sun. It doesn't, by the way, as far as we know, have any planets. But amongst the 100 billion or so stars in the Milky Way, there are probably at least 1,000 others that were born at the same time as the sun. And a European spacecraft called Gaia has been mapping the nearest 2 billion stars, partly in the hope of finding these. I wanted to mention it today, partly because it's the subject of next month's lecture, which you should all come to, but also because Gaia ended an 11-year mission of mapping the sky about an hour ago. And so I've got a month to read up on 11 years worth of observing the sky. But one of the things it was built to do was to find our solar siblings and find out if the sun is unusual. I want to leave you with one final perspective. I've talked about Parker that flew as close as possible to the sun, but I also mentioned that we have these spacecraft, Voyager 1 and Voyager 2, out on the edge of the solar system, and they're carrying out scientific observations using equipment that's running on a shoestring. They don't have much power left, but they're able to monitor the unusual environment they found themselves in, because both of the Voyagers seem to have passed through what's called the heliopause, the region on the edge of the solar system where the sun's influence ceases to be dominant. And these spacecraft are now sailing through the galaxy, exposed to the interstellar environment. They still feel the sun's influence, but they're also out in the big wide world. But this was a source of frustration for most of a decade, because NASA kept saying that the Voyagers were about to cross the heliopause. It wasn't clear whether they had done. One day it would look like they were in interstellar space, the other they'd be back firmly within the solar environment. And what we've realized is that this edge of the solar system, drawn in this lovely artist's impression as a nice smooth bubble, is actually a complicated place. Of course it's complicated. It's made by the sun, which you know is complex, but also because it's built up by these coronal mass ejections and this material that storms out through the solar system in a deeply nonlinear fashion. And so what happens on the edge of the solar system, way beyond Neptune and Pluto, which is not a planet, but out on the outer edges of the solar system, what you get is a build-up of bubbles sent from the sun via these violent processes that we're only now able to understand, creating a complex border which we've just managed to send 2 craft sailing through to explore. Between them and the thing moving faster than anything else, we're slowly getting to the point where we actually understand the true complexity of our star. Thank you very much.
Right, now we'll look at how do we know how long the sun has to go in its life cycle. And this one I think goes for about 20 minutes, and then 2 or 3 minutes on the difference between the ESA Solar Orbiter and NASA's Parker probe before closing.
Now, you'll often hear people say that the sun is about halfway through its life and that it's got maybe 5 billion years or so left to live before it runs out of fuel. Where does that number come from, though? Because the calculation itself is actually not that difficult, but we have to know so many things that layer on top of each other before we can even hope to get at that number. So what I'm going to do is I'm going to go through the calculation, back of the envelope calculation, nice and simple, for how we get to that rough estimate of the fact that the sun has about 5 or so billion years left to live. Every time I say something that you're going to be like, wait a minute, how do we even know that? I'm going to raise a little flag. I'm going to make a list of all the things that we need to know in order to work out how long the sun has left to live. And I'm going to come back and explain how we even know that in the first place. Okay, so to work out how long the sun has left to live, we first of all need 2 things. We need to know how massive the sun is and how bright the sun is, something we call its luminosity. How much energy is it giving off per second? Now, the sun's mass is 2 times 10 to the 30 kilograms, or 2 with 30 zeros after it. Its luminosity is 3.8 times 10 to the 26 watts, or joules per second, energy given off by the sun per second. And with these 2 numbers, we can use one of the most famous equations in the entirety of physics. I'm talking about Einstein's E equals mc squared. Mass and energy are equivalent. So if you have something with mass m, then you can turn it into energy E. So assuming that the sun powers itself with fuel that it has inside of it, we can assume that the sun's mass is its fuel for its energy. And so with E equals mc squared, we can work out the total energy that the sun would have, plugging in those numbers. We can then divide that by the amount of energy it's giving off per second to get how long the sun will live in total in seconds. Then we can convert that to years, and we get an answer that is far too big. Now the reason it's too big is because that calculation has assumed that the sun's entire mass, i.e. all the stuff that's in the sun, will be available to use as fuel for it to burn, to give off light and heat and energy, which we love because it allows us to have fun days at the seaside. But that's not the case. The way the sun powers itself is by nuclear fusion. It takes atoms of hydrogen and fuses them together to make helium, and in that reaction energy is given out, and that's the energy that we then receive on Earth. The thing is, it's only hot enough in the very center of the sun for those reactions to take place. You need a tremendous amount of energy to force 4 hydrogen atoms together. So actually nuclear reactions are only taking place in the core of the sun, which is about 10% of its mass. If we use 10% of 2 times 10 to the 30 kilograms, we still get too big of a number out from our calculation. But some of you might have picked up already on the reason for that. It's that the hydrogen in the sun that it's using as fuel isn't purely converted to energy like E equals mc squared assumes. Some of it turns into helium. You need 4 hydrogen atoms to make 1 of helium. And a helium atom is actually 99.7% of the mass of 4 hydrogen atoms. So actually only 10% of the total mass is useful for nuclear fusion, and you'll only get 0.003 of that mass converted to energy. And if we use those numbers, then we get out that the sun has about 10.5 billion years worth of hydrogen fuel available to it. But that's the total lifetime of the sun, not how long the sun has left to live. To work out that, you have to know how old the sun is already. And we know that that is 4.5 billion years old. So if you take one from the other, you get about 6 billion years old, which for a back of the envelope calculation is not bad. If you do it properly with all of the modeling, then you come at the sort of more agreed value of say like 5 billion years or so. But, you know, what's 1 billion years between astrophysicists and friends? So back of the envelope calculation done. Here's our list of 7 things that got flagged that I said that we needed to know in order to be able to do that calculation. And I think you'll agree it's quite a long and interesting looking list. And probably a lot of you will be wondering, yeah, how did we work those things out? So first up, the mass of the sun. How do you calculate how much stuff is in the sun when we're stuck on Earth? The fact that the Earth is in orbit around the sun, though, means that the gravitational force pulling the Earth inwards towards the sun is perfectly balanced by the centrifugal force pushing outwards on the Earth. Now, just like you do when you get on a merry-go-round. And if you've been on a merry-go-round, you know that you feel that force pushing you off the merry-go-round as you go faster and faster. And so by balancing those equations, we can see that we can measure the mass of the sun if we know how fast the Earth is moving and at what distance it is from the sun. And then also this gravitational constant, which was first sort of accurately measured properly in a lab by Henry Cavendish. Now, we obviously don't know the speed the Earth is moving around the sun, but speed equals distance over time. And the time that the Earth travels around the sun is Well, a year, 365 days, or 365.25 days. Anyway, we know that. The distance it travels is just the circumference of its orbit, which if we assume is circular, and you remember your high school maths, is just 2 pi r. Of course, actually, the orbit of the Earth is sort of more elliptical shape, but let's go with circles right now because it's just a little bit easier in terms of the math. And so then we can cancel out that speed that the Earth goes around the sun just to get an expression in terms of the distance of the Earth from the sun, and then also the time it takes to go around and this gravitational constant again. So, okay, we only need to find the distance from the Earth to the sun to measure how massive the sun is. How do you get the distance from the Earth to the sun, though, is therefore the next question. Measuring the distance to objects that aren't solid is very difficult, but solid things, we can do that dead easy, right? We do it all the time with air traffic control that use radar. Radar takes radio waves and it bounces it off the solid object, comes back. You know the speed that the waves have traveled at, so the time delay gives you the distance. But the sun is not solid. It's a plasma, which basically means that it's like a gas, but the electrons aren't in orbit around the atoms anymore. They're just like freely roaming. So you've got sort of like a charged soup of particles, basically. So we can't use radar to measure the distance to the sun, but we could use radar to measure the distance to solid objects in the solar system, like other planets, for example. And if we think about the setup of Earth going around the sun and say Venus or Mercury going around the sun, then there's a special place in Venus's and Earth's orbits where they make a right-angled triangle with the sun. So if you wait for Venus to get to that point and it makes this perfect right-angled triangle, you can measure the distance between Earth and Venus easily because it's a solid and it'll bounce the radio wave back off nice and easy. You can then measure the angle between Venus and the sun in the sky at that point, and then it's just trigonometry to work out that distance between the Earth and the sun. So all you haters on trigonometry out there that's like, trigonometry is not useful outside of school. Well, it is. To me anyway. Next up, the luminosity of the sun. And you think this would be an easy thing to measure because you're just measuring the amount of energy you get from the sun per second, which you can do if maybe you say leave a pot of water out in the sun and see how quickly it heats up, for example. You could measure the amount of energy you're getting. The thing is, you're only measuring the amount of energy that reaches us on Earth. So the total output from the sun will go out into a sphere, and then we'll only measure that tiny cross-section that intersects with your pan of water or your solar panel to measure the amount of energy we're getting. That's something called the flux rather than the luminosity. Flux is proportional to the luminosity divided by the distance to that object squared. Now, we just talked about how we get the distance from the Earth to the sun, so if we just measure the flux of energy we receive on Earth, we can then easily get back to the luminosity of 3.8 times 10 to the 26 joules per second. Next up, E equals mc squared. Einstein's most famous equation. In fact, probably the most famous equation in the world. But how do we know that energy and mass are equivalent? And how do we know that you happen to times the mass by c squared? It all comes from a consideration of how much energy things at rest compared to things that are moving have. So you'll have learned at school that kinetic energy, things that are moving, have an energy of a half mv squared, so their mass times by their velocity squared. But photons don't have mass, and yet when they're moving at this incredible speed, they still have energy and momentum, so that kinetic energy formula doesn't really work. So if you work through all of the maths of what the energies of different particles with mass and without mass have, which is actually just high school maths, it's not overly difficult, then you actually come down to the conclusion that an object completely at rest will have the energy equal to its mass times by c squared. Now, I'm not going to go through the maths here because that is probably a whole video by itself, but if you are super interested in that, Ethan Siegel from Starts With a Bang has a fantastic article on it, and I will link it down below. So number 4 on our list, that the sun is powered by nuclear fusion, is kind of intrinsically linked to number 6 on our list, that a helium atom is 99.7% of the mass of 4 hydrogen atoms. We kind of needed one to figure out the other, but it's a little bit of a long story how that was actually figured out. And it starts in about 1904 when Ernest Rutherford discovered the enormous amount of energy released by radioactivity, specifically alpha decay, when an atom of an element can essentially decay into a lower mass element, and it does that by giving off what we call an alpha particle, something that's 2 protons and 2 neutrons, just like in a helium atom. And the fact that so much energy could be given off by a nuclear process made people think, well, perhaps that's what's powering the sun, this thing that's giving off an enormous amount of energy. But it was only very heavy elements that underwent this radioactive decay, things like uranium, plutonium, the elements that their atoms are so chock full of protons and neutrons that it's just really difficult to hold them all there. Now, if that was the case, if the sun was powered by these very heavy elements, then we should be able to detect the presence of those elements in the light we get from the sun, because all elements sort of leave a quantum fingerprint on light, because either they absorb a specific wavelength of light, and that's very obvious when we take the light from the sun and we split it through a prism, through a spectrum. This is exactly what happens when you get a rainy day or a waterfall and the light is split through those little water droplets and forms a rainbow. What you don't see though are the very, very specific wavelengths of light that are actually missing, because in a rainbow they all sort of blur into one. But if you can get the resolution to see it, you see that that rainbow actually has gaps in it, dark bits where we don't see that very specific colour. And it's because an atom of a specific element that's in the sun has absorbed it. But when you look at those specific wavelengths and you correlate them with the wavelengths of absorption of light we see on Earth when we look in the lab, you find that it's mostly hydrogen and some helium. And so people quickly realize that actually those heavy elements aren't present in the sun at all, and that the sun therefore couldn't be powered by radioactivity. It was then in 1920 that a British physicist called Aston actually managed to measure the masses of individual atoms of elements. So he managed to very, very precisely measure the mass of a hydrogen atom, a helium atom, and so on through the periodic table. And he did that using a really clever device called a mass spectrometer. And a mass spectrometer is sort of like a chemist's best friend. I haven't really thought about them since A-level, so this was fun doing this research for this video. But essentially what happens is you first of all take out an electron from around an atom. And by removing an electron, you've removed some negative charge, so you've positively charged the atom that you then have. You then fire that atom through the mass spectrometer instrument where you've set up a magnetic field. Now, electric charges moving in magnetic fields, they have their paths deflected. They have their paths curved. But the amount that it's curved depends on how heavy the thing is that's moving. So if you send a hydrogen atom down there, it'll curve much more than, say, a helium atom would that is heavier than a hydrogen atom, even though they've got the exact same charge by just removing one electron. And with this, you can measure incredibly precise masses of the elements. What was surprising to chemists at the time, though, is that the elements' atoms weren't just pure multiples of each other, but it took Arthur Eddington making the connection between that mass difference and E equals mc squared to realize that if you could take 4 atoms of hydrogen and somehow fuse them together so that they became an atom of helium, then you would give out that tiny difference in energy. But if you had enough hydrogen, then you could get out an enormous amount of energy by doing that. Now that's great, but it really was only a hypothesis. There was no way that you could actually therefore test the fact that that was going on in the sun, except for the fact that you saw that the sun was mostly made of hydrogen and some helium. Now, through the 20th century, many physicists worked on the actual theory of what would physically happen in that process of taking 4 hydrogen atoms and making it into 1 helium atom, because it's not necessarily as simple as it sounds. So that included Gamow, Atkinson, Hooterman, and Weizsäcker. In the process, yes, you formed the helium, but you also released 2 electrons, 2 electron neutrinos, and then some energy. Now, the hydrogen and helium we can't detect. But what about the neutrinos? Neutrinos are incredibly, incredibly tiny, very small mass particles in the standard model of particle physics. And they're not really impeded by anything. They can just go through everything in their path. And so getting out of the sun is actually relatively easy for them. They literally stream out of the sun from these nuclear reactions. And we only know that because people eventually detected those neutrinos on Earth from the sun. It then meant all the evidence pointed towards nuclear fusion as the process powering the sun. So I guess we skipped number 5 on the list there, that the inner 10-ish% of the sun is actually hot and dense enough for these nuclear reactions to occur, forcing these hydrogen atoms together to become helium. Now, how we figured that out kind of all falls under the umbrella of helioseismology. So helio, meaning the sun, as in Helios, the sun god in Greek. Or is it Latin? I think it's Greek. It might be Latin. And then seismology, which might be a word you recognize from people studying earthquakes. And it's using those earthquakes that we've been able to figure out what the interior of the Earth is like. So what about sunquakes? It has waves propagating through it all the time. And the closest sort of analogy really is a sound wave propagating through the sun. We like to say the sun rings and you can listen to it. And by listening to all the different frequencies that you get as all those waves ping around the interior of the sun, interfere with themselves and set up this weird pattern that we can then unravel with some really clever maths. You can then figure out what's going on in the interior because the pattern depends on how fast the waves are moving and what they're moving through. And they speed up and slow down depending on the temperature and pressure of the stuff that they're moving through. So by producing that map and unraveling all the frequencies that we hear from the sun, we can get an idea of what the temperature and pressure is actually like inside the sun. Using that map, we can work out that only the inner 10%-ish is hot enough and has a high enough pressure to be able to force atoms together. And knowing what that temperature and pressure has to be all comes from quantum physics and understanding the behavior of atoms on the very, very tiny scales. Again, that wouldn't even just be a single video. Like if you want to understand quantum physics, I'd recommend doing an undergraduate degree in physics. But maybe one day I'll tackle a video on that. And so with all that information and assuming that the sun will start off as a pure ball of hydrogen and be able to use all that to convert it to energy in its lifetime, we get the total lifetime of the sun. But that's not how long the sun has left to live. For that, we need to know the last thing on our list, which is the age that the sun is now. It's not something we can really get from studying the sun. You know, it's not like a tree that we can cut down and count the rings. But what we can assume from other sort of planetary systems and new stars forming in the rest of our galaxy in the Milky Way, we can assume that the sun and the planets and everything else in the solar system all formed at the same time. So if you can measure the age of another object in the solar system, then you can get at the age of the sun. Now, we could try and find some of the oldest rocks on Earth, but most of the rocks on Earth will have been pre-processed because of the fact that, well, we have, you know, volcanoes and plate tectonics that sort of like melt down rocks and reform them. So really what we need is a relic from the very early days of the solar system that has sort of been left alone pristine from its very first formation. And luckily, we have those in the form of asteroids that then fall to Earth as meteorites. Now, in those meteorites and asteroids are those very heavy elements like uranium and plutonium that undergo this radioactive decay. So, for example, uranium decays into lead. So if you know the rate at which that happens and you can measure how much lead there is, then you should be able to work out how old it is, except for the fact that you don't know how much uranium you started with. But what if we had 2 different types of uranium that decayed at 2 different rates into 2 different types of lead? Then what we'd end up with is 2 different amounts of lead that have arrived at that point at 2 different rates, and that would allow you to get at how old that object is. Now you're probably thinking, how can you have a different type of uranium, Becky? It's an element, it's the same thing, it's just uranium, right? But if you add extra neutrons to an atom, you make something which is called an isotope. It's the same element, it's just a little bit heavier with those extra neutrons. And so that's what makes it decay at that different rate, because you've actually got a more unstable atom by adding those extra neutrons. So by working out the ratio of the two different lead isotopes you get in the end products, you can get at how old the asteroid and therefore the solar system and therefore the sun is, which you find is about 4.5 billion years old. Phew! So that was all the information we needed to answer that one question. How long does the sun have left to live? It's incredible when you think about it, like how many results and even different areas of science had to come together for us over centuries of research for us to be able to answer that question. So next time you hear someone say the sun is halfway through its life or has 5-ish billion years to live, I hope you'll think about all the human effort and centuries of work that went into producing just that one number.
We'll close with the solar orbiter set to some music called True Power, and it's currently 17 degrees below the ecliptic, so 17 degrees below the plane of the planet, such that it can see the South Pole, but I believe it is going to move to be a little bit further south as well. Some pretty good engineering to actually withstand that close. And as they said, they couldn't image it with the Parker one because it comes too close to the surface and we don't have the instrumentation to do it. And with that, we'll close the meeting and hopefully we'll see you at the July meeting. Thank you.